Hello everyone, my name is Kyowon Jeong, a postdoc in Kolbach Lab in University of Tübingen in Germany. Today I'm going to present our recent work on FDR control in proteoform identification via top-down proteomics. As shown in the title, I will present the effect of errors in precursor mass determination upon the FDR control. Before I begin, I would like to thank to the ISMB organizers for giving me such a wonderful chance. I believe most audiences are already familiar with top-down proteomics or TDP since it is getting more and more attention recently. But let's quickly review TDP as compared with bottom-up proteomics or BUP. This sausage illustrates an intact protein molecule. In conventional bottom-up proteomics, the protein is digested into short peptides, and from each peptide, spectrum is generated. On the other hand, in top-down, intact protein is analyzed as is without digestion. Top-down proteomics is therefore suitable to study proteoforms. Proteoforms are the different forms of protein produced from a gene with genetic variations or post or co-translational modifications. Since proteoforms provide higher resolution and closer to phenotype information than proteins, they are gaining more attention in medical and clinical researches. And since top-down methodologies analyze intact proteoforms as a whole, in theory, we can retain the proteoform level information, which are lost when we use a too small magnifying glass, referring to a conventional bottom-up approaches. Okay, then how the actual peaks from proteoform ions look like. Now we shortly come back to peptide ions before we see proteoform ion signals. Due to relatively small masses, peptide ions often have small charge values, and also they usually come with small numbers of isotopes. But in case of proteoforms, they generally have wider charge ranges and so many isotopes. So a single kind of proteoform ion often results in more than 100 peaks in spectrum. This illustration shows only 3 charge states, but we often observed more than tens of charges from a single kind of proteoform. And when multiple proteoforms are present in the spectrum, more charged ions will be there along with their isotope peaks. And unfortunately, we don't have any colored peaks as in the previous illustration. In other words, we do not know if a peak is from which mass or with which charge and so on and so forth. So the first step in top-down data analysis is usually to find the proteoform masses that generated this complex spectrum. This reverse engineering from spectrum to masses is called spectral deconvolution. This is one example of top-down spectrum from only 6 proteins. The red peaks are the peaks from a single mass of 50 kilodalton, but with different charge states. And below is another example for E. coli DNA polymerase with 68 kilodalton mass. This kind of redundant and complex signal structure necessitates the deconvolution step in most top-down analysis. Now let me talk about the effect of deconvolution to the identification, in particular the effect of false positives in deconvolution. Let's see the typical proteoform identification pipeline, starting with the deconvolution. And the output from deconvolution, deconvolved spectra are then used as inputs to the database search to find hopefully correct PRSMs. PRSMs meaning proteoform spectrum matches. And we always have uninvited guests, false PRSMs. In most top-down identification pipeline, the FDR control is done during the search. If we skip the first part in the deconvolution, then this is almost identical with the bottom-up peptide identification pipeline. So we expect FDR control effectively remove these false PRSMs as in the bottom-up case. But we do have deconvolution step, and again we have uninvited guest, falsely deconvolved spectra. These false ones are used as inputs to the same database search without any distinction from our side, again generating many false PRSMs. Then the question is, does the above FDR control effectively remove the second kind of false PRSMs, right? But before we move on, let me point out this. False deconvolution can happen in precursor mass determination and or fragment mass determination. If we have a super well annotated data set, so-called gold standard data sets, then everything will be quite easy. But in top-down area, we don't have enough such standard data sets yet. One thing you can try in this situation is to introduce false deconvolution results on purpose and see if they are removed by FDR control. We may introduce precursor mass error by simply adding random masses, for example, between -10 to 10 Dalton to the deconvolved precursor masses. They will be used for search, yielding many false PRSMs. Likewise, we can introduce false fragment masses for another set of false PRSMs, and both precursor and fragment false masses. Now these false PRSMs in each of three groups were compared against decoy PRSMs from a normal search. Normal search meaning we didn't manipulate the deconvolution step. If decoy and false PRSMs have different score distributions, then you can notice there will be FDR bias. Now this is the empirical cumulative distribution in open search, top-down open search. Let's focus a little bit. The blue curve is the target distribution from a normal search, so good ones, and the red one is the decoy distribution from normal search. The purple one, it is the case in which precursor and fragment masses are false. Green one, only fragment masses are incorrect. Lastly, the bright blue is the false precursor mass case. There are so many cases, but there are only two groups. The left orange circle, decoy and purple green ones, they gather together. They are quite similar. It means that FDR control works for those purple and green cases. On the other hand, look at the circle in the right side. Bright blue is very close to blue. Bright blue is supposed to be close to decoy, in other words, red. So this bright blue case is not controlled by target decoy-based FDR. Now we remember, bright blue is the false precursor mass case. The same experiment was done for bottom-up open searches. Similar symptom was observed, but bright blue precursor mass error was not as close to the target as in top-down, meaning this issue is more serious in top-down than in bottom-up. Then why this is happening? What happens if precursor mass is incorrectly determined in top-down? This is an example of fragment mass mapping in high-quality proteoform identification. Another one, and another one. If we compare them with fragment mapping in bottom-up, we easily realize that we have quite rare complementary ion pairs in top-down. In bottom-up, if precursor mass is incorrect, we lose for sure prefix or suffix ion matches. But at the same time, in most cases, immediately these complementary ion pairs are also lost, bringing a huge drop in match scores. But in top-down, we will lose either prefix or suffix ions, but we do not lose many complementary ion pairs because there are not so many already. So in top-down, precursor mass errors do not affect match scores as much as in bottom-up. Therefore, in most cases, false identifications with precursor mass errors have relatively high scores in top-down as compared to bottom-up, which are not modeled by decoy hits. Now we know if precursor masses are incorrect, we are in trouble. But then how often do we have such errors? In bottom-up area, errors in precursor chart determination have been known, and in top-down as well, the community is well aware of the convolution itself is quite error-prone, and we don't have a robust error control for the convolution at this moment. But we may need a direct evidence that actually we do have frequent precursor mass errors. One simple method to check it is to compare two different pipelines for the same dataset. Two pipelines have different deconvolution methods, 1, 2, but the same database search. We applied the 1% proteoform level FTR control via target decoy. So after the analysis, we have 1% FTR controlled identification sets, PRSM 1 and 2. From the obtained PRSMs, we go back to the spectra. From all MS2 spectra, this portion was identified by pipeline 1 and this green by pipeline 2. If FTR is indeed 1%, what can we say about this jointly identified spectra? Their identification consistency should be over 98%. Using this criteria, FTR lower bound can be obtained by measuring the identification consistency for the overlapping spectra with this simple formula shown below. First, we performed an open search. From the above overlapping area, we had almost 4,000 overlapping PRSMs, and out of these, 3,800 had the same protein accession. So the FTR bound at the protein level is 2%. Likewise, 3,200 or 300 had the same sequence. So at sequence level, FTR bound is 9%. It's already a bit too high. Lastly, at proteoform level, we had almost 20% FTR bound. The red flows are the inconsistent parts. Then where are they from, these inconsistent parts? As expected, most of the red flows are connected to the inconsistent precursor deconvolution results, color-coded by orange in the right side. This means that these inconsistencies are mostly from precursor deconvolution inconsistencies or deconvolution errors. And that means uncontrolled false positives at sequence and proteoform levels are due to these precursor mass determination errors. And for sure, from the large portion of orange, we can clearly see that the precursor mass is often incorrect. Then we also performed a search without any modification allowed. We can expect far less precursor mass errors in these searches. And now we have 1,800 overlapping spectra. When you repeat the previous FTR bound calculation, we have far better situation now. At all levels, FTR is not too biased. From the above open search case and this case, and also from the previous distribution comparison analysis, we can deduce that for the precursor error-free identifications, FTR via target decoy is rather accurate in all levels. Now we can say that FTR control works only for the false positives on the top, right? Some of false PRSM from false deconvolution remain. Then the fundamental method should be to control precursor error during the deconvolution to prevent such errors, deconvolution errors, and in turn prevent false PRSMs. Now I want to present a new proteoform level FTR calculation that takes precursor errors into account. We bring this observation above. For precursor error-free PRSMs, FTR via target decoy is accurate. Now this gray circle is all proteoform IDs. Out of them, blue portion is the precursor error-free zone. Remember, in this remaining gray area, all proteoform IDs are incorrect. Blue over gray is 1 minus correctly deconvolved precursor masses divided by all deconvolved precursor masses. Okay, and it can be shown as like 1 minus precursor deconvolution FDR, or simply 1 minus P FDR. Now, from the above observation, we can say in this blue region, proteoform level FDR is similar to FDR by target decoy, which is FDR TD. In other words, if we have the green portion, which is two positive IDs, the ratio between green and blue is given by 1 minus FDR TD. So lastly, for the proteoform level FDR, it can be calculated by 1 minus true positive IDs divided by all proteoform IDs. And it can be expressed by this simple diagram. And if we have all the ratios there, so we have the final formula. But still, this PFDR is unknown. We recently developed an estimation method within our flash decomp software, which will be presented elsewhere. So in summary, deconvolution error in precursor mass determination propagate to false positive proteoforms, and they are not controlled by target decoy-based FDR estimation. And to address the proteoform level FDR bias, we presented a corrected FDR calculation formula that needs FDR estimation of precursor deconvolution, or PFDR. The presented FDR calculation is rather a lower bound, which needs to be evaluated when so-called gold standard datasets become available. And deconvolution FDR estimation of PFDR, will be presented in near future. This work is submitted to proteomics and under revision, and you can also find the preprint. And finally, I want to thank to my PI Oliver Kolbacher and my colleague Jihyung Kim in University of Tübingen, and I appreciate all the helpful discussion and help from other lab members who co-developed our software suite OpenMS. Also, this work has been done with Philip in Tolle Lab and Kiel University, and Dr. Won-hyuk Jeong in Gupta Lab in Yale University. I thank them all. This work has been funded by EPIC Access and Ministry of Science, Research and Arts in Baden-Württemberg. Lastly, I thank to the audience for your attention and will gladly take any question. Thank you.